Okay, I'm just going to cover some more advanced types of limits that we might see. And the first one that I want to cover is an equals, let's say, sine of n divided by 2 to the n. And for this one, you actually cannot use calculus limits exactly, at least not the way you think. I think that maybe in Calc 1, you remember the squeeze theorem, which says that if, well, how about we just do it directly? So notice that sine of n is actually bounded as an envelope by 1 and -1. So in fact, an is less than 1 over 2 to the n, and it is larger than -1 over 2 to the n. So both of these go to 0. So that means an goes to 0 by the squeeze theorem. The pictorial version of what's going on here is actually this. This is what sine of n divided by 2 to the n actually looks like. It looks something like this. So it's oscillating, but the oscillations are damped. So then, and here's the envelope of 1 over 2 to the x and -1 over 2 to the x. You can see they're forcing it to go to 0. So, or squeezing it to go to 0. So you're free to use the squeeze theorem, but squeeze theorem is really useful for oscillatory things. So squeeze theorem for oscillations. So here's another example, -1 to the nth power divided by n. You can use the squeeze theorem for this limit. It should be 0 again. Okay, next example that I want to cover. I'm sorry. Let me just go back to this one for a sec. The reason you can't use calculus limits for this one is because the limit, of course, of sine of n as n goes to infinity, it shouldn't exist, really. So you can't just do 0. You can't just do like 1 divided by 2 to the n. Or I'm sorry, you can't just use directly evaluate the limit. So that's why you need squeeze there. Okay, let me move on. So another advanced kind of limit is anything involving factorials. So as it turns out, all we need to do, for example, let's consider this problem. 2n factorial divided by n factorial squared. So this is our an. So to evaluate limits like this, we're going to introduce the following test. If the ratios as n goes to infinity, if this is less than 1, then it implies an goes to 0. If it's greater than 1, it implies an goes to infinity, or at least the absolute values go to infinity. So, and if it's equal to 1, it's just inconclusive. So this is basically saying this test can be thought of as how geometric is it? Or how exponential-like is it? So remember, if I had an equals x, then our successive ratios is just absolute value of x. So if this is less than 1, then absolute value of x to the n goes to 0. If this is greater than 1, then absolute value of x blows up. And if it's equal to 1, well, it's actually inconclusive because minus 1 to the nth power, that certainly qualifies, but this does not have a limit, whereas 1 to the nth power goes to 1. So the test just doesn't tell you anything in those cases. Let me just recall, why does x to the nth power go to 0 if absolute value of x is less than 1? This is just like, it's like 0.1 to the nth power. And so this is 0.1, this is 0.01, this is 0.001. And so this should go to 0. And so in general, in base 1 over x, so this, remember, this is base 10. So we're using a decimal expansion. If I use a 1 over x expansion instead of a decimal expansion, it's just the same as above. But like in binary, if I use base 2, then 1/2 to the nth power also has this expansion. So it's the same idea. So that isn't like a rigorous proof or anything, but yeah, I hope it's very plausible that limit is true. Okay. So now that we have this test figured out, let's apply it to this example right here. So now we're going to apply the test to an equals 2n factorial divided by n factorial squared. So here's what I'm going to do. I'm just going to first write out an plus 1. So that means you replace n with n plus 1 everywhere you see it. So 2 times n plus 1 factorial divided by n plus 1 factorial squared. So now I'm going to expand this. So this is 2n plus 2 factorial divided by n plus 1 factorial times n plus 1 factorial. So now we're going to evaluate the factorials. So 2n plus 2, it's the recursive, remember? So it's the same as the previous one, and you should multiply by the number. So 2n plus 2. And I'm going to use it one more time. So then this is 2n factorial times 2n plus 1, the previous number, and then it's 2n plus 2. So this is actually what we started with. Remember, we started with 2n factorial, and so we have 2 extra terms, not 1. This is probably a mistake that I've seen quite a bit. So n plus 1 factorial, on the other hand, squared. That should be straightforward. This is just n plus 1 squared times n factorial squared if I just use that expansion one time. So overall, an plus 1 should just be 2n factorial divided by n factorial squared if I just collect this term and this term, and then I just add the extra stuff. The extra stuff is 2n plus 1 times 2n plus 2 divided by n plus 1 squared, namely this term and this term. So this is actually an. This is an, and then extra stuff. The extra stuff is 2n plus 1 over 2n plus 2, and then we have an n plus 1 squared. So I'm just going to now go to evaluate this limit. So I know that an plus 1 is an, the original thing, times this extra stuff. And really, I just need to evaluate the extra stuff because remember, our ratios, how geometric it is, that's what we're looking at here. An plus 1 over an is 2n plus 1 times 2n plus 2 over n plus 1 squared. So I just need a limit of these ratios. So remember, I'm going to factor out the big thing. So that's 2n times 1 plus 1 over 2n. And then we have another 2n times 1 plus 1 over n, all over n squared times 1 plus 1 over n squared. So let me just clean that up a little bit. So this is the limit of 2n squared divided by n squared times 1. You can all tell that all these go to 1. This goes to 1. This goes to 1. this goes to 1. So all we need to do is just think about this, the big stuff. And the big stuff is just 4. So that's 4 times the limit of other stuff. I hope you don't mind if I skip some steps here, but it should be clear that 1 plus 1 over 2n plus these other terms should go to 1. If not, I would totally just check that work, see if I did this correctly. So I claim then that our limit is 4, and so this is saying that an plus 1, it's roughly speaking, it looks like 4 times an, and so an is roughly like 4 to the nth power. So in that case, it goes to infinity. Okay. So that means our original limit. So therefore, the limit, because of our test, by the test, limit as n goes to infinity of an is actually infinity. It blows up. Okay, and that's, you can think of it as like a ratio test. And so those are very useful for factorials or exponentials. Okay, thanks for watching.